In this lesson, we will learn all about the properties of exponents. Exponentiation is a mathematical operation involving two numbers, in this case the base 3 and the exponent or power 4, and pronounced as 3 raised to the fourth power. When the exponent is a positive whole number, exponentiation corresponds to repeated multiplication of the base. That is, 3 to the fourth is the product of multiplying 4 3's together. Let's take a moment to evaluate some expressions with exponents in them. First, we have 2 to the fourth power. 2 to the fourth power is the same as multiplying 2 by itself 4 times. So 2 times 2 times 2 times 2. And because this is multiplication, we can do it in any order. So 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 2 to the fourth power is 16. Now, negative 2 to the fourth power is as if we were multiplying negative 2 times itself 4 times. So negative 2 times negative 2 is positive 4. Positive 4 times negative 2 is negative 8. And negative 8 times negative 2 is positive 16. When you multiply a negative number by an even exponent like 4, the product is positive. In expression number 3, we have negative 2 to the fourth, but this looks a little different than in expression number 2. In expression 2, the entire quantity, negative 2, is being raised to the fourth power. Here, we have a negative sign and then a 2 to the fourth. So the only thing in it that actually has an exponent of 4 is the 2. That negative sign in the front is like a negative 1 multiplied by 2 to the fourth. So in this case, when we multiply, the number we're going to multiply it by itself 4 times is just a number 2 and the negative sign will be in front. Here, I'll show you. This is like saying negative 1 times 2 times 2 times 2 times 2. Because the exponent only references the base number directly in front of it. Now, if we were to multiply all these out, the 2 times 2 times 2 times 2 is going to be 16 like it was in the previous two expressions, but we have a negative 1 in front, so negative 1 times 16 is negative 16. If we wanted to multiply the entire negative 2 by itself 4 times, we would have to put the negative 2 in parentheses as in expression number 2. For number 4, 2 to the third power is 2 times 2 times 2. And since the expression is just a 2, there's no symbol in front of it. We could just multiply 2 times 2 times 2. 2 times 2 is 4. 4 times 2 is 8. Now in expression number 5, we have the quantity 1/2 raised to the fifth power. Now, because the 1/2 is in parentheses, everything in there gets raised to the fifth power. So it's going to be 1/2 times 1/2 times 1/2 times 1/2, and then a fifth one times 1/2. Now, remember, multiplying fractions, you multiply all the numerators by each other, and then put that over all the denominators multiplied by each other. So the numerator should be pretty easy. 1 times 1 times 1 times 1 times 1 is 1. And 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. And 16 times 2 is 32. So 1/2 to the fifth power will be 1 over 32. Now, there are several properties of exponents that will govern how we use them in algebraic expressions. The properties of exponents we will be reviewing in this lesson are the product of powers, the quotient of powers, the power of a product, the power of a quotient, the power of a power, the zero exponent, and a negative exponent. So let's look at those individually. The product of powers property occurs when you're trying to multiply two powers that have the same base. So the base x in both of these, When they have the same base and you're multiplying them together, you will add their exponent values. So as an example, 2 to the third and 2 to the fourth both have a base of 2. Even though their exponents are different, that's okay. We're going to add them together. 2 to the third and times 2 to the fourth is 2 to the seventh. And to see why this works, let's break it apart into different pieces. 2 to the third is like writing 2 times 2 times 2. And then 2 to the fourth is like multiplying 2 times 2 times 2 times 2. Oh, wow. We're just multiplying 3 2's by 4 2's. So together that is 1, 2, 3, 4, 5, 6, 7 2's. So it equals 2 to the seventh. That's pretty cool. And that's how it works. So the shortcut of that is if you have two numbers being multiplied and they have the same base, even if their exponents are different, you can multiply them together by adding their exponents. So let's see how this works with a combination of numbers and variables. So below we have 2x squared times 3x to the fourth. Well, this is a multiplication problem, so I can actually split this up into all of its individual pieces. I could say 2 times x, and that's another way to write 2x squared. Then I can write 3 times x times x times x times x, and that's another way to write 3x to the fourth. And since everything in this problem is being multiplied, it really doesn't matter what order I do things in. There is the commutative property of multiplication, which says I can solve it in any order I want. So I'm going to choose to multiply the numbers that are whole numbers first. So 2 times 3 is 6. Then I will calculate how many x's I really have multiplied by each other. I have 1, 2, 3, 4, 5, 6. So this can be rewritten as x to the sixth. Now, using the product of powers property, we could have more simply multiplied 2 times 3 and gotten 6, and then x squared times x to the fourth. 4 plus 2 is 6. That would be x to the sixth. The quotient of powers states that if you are dividing two powers that have exactly the same base, you can subtract their exponents to find their quotient. So if we have x to the m over x to the n, that will equal x to the m minus n. But in a numerical example, 3 to the seventh over 3 to the third, you can subtract their exponents. 7 minus 3 is 4. That will equal 3 to the fourth. Now, how this actually works requires us to break apart these problems. So let's do that. We have 3 to the seventh. That's 3 times 3 times 3 times 3 times 3 times 3. That's 6 times 7. All over 3 times 3 times 3. So that's 7 threes on top of 3 threes. And these threes on the top and threes on the bottom can cancel each other out. You've been doing this for a long time, of reducing fractions by canceling terms. And we will do the same thing here. So if we have 7 threes on top and 3 threes on the bottom, these 3 threes on the bottom can cancel out 3 of the threes on top. And what are you left with? 3 threes on the top of your fraction. So 3 to the fourth on the top over 1, which is just 3 to the fourth. So the quotient of powers property is a shortcut to doing this canceling action that we have been doing for a while. Now let's see how this works with an expression with numbers and with variables in it. So first we have 6 over 3. And I can rewrite 6 over 3 as 2 times 3 over 3. And this is where our original canceling properties came from. We can cancel out the 3 on the bottom with the 3 on the top and be just left with that 2. But we are not done, because there are 1, 2, 3, 4 x's on top being multiplied, and 3 x's on the bottom. So we have 4x's on top, 3x's on the bottom. Each one on top will cancel out one on the bottom. And we're left with just an x on the top. So 6x to the fourth over 3x to the third is 2x to the first, or just 2x. Now, how could we use the quotient of powers to simplify that? Well, the 6 over 3 doesn't simplify any faster using the quotient of powers. However, x to the fourth over x to the third, 4 minus 3 is 1. That's our x to the 1 that we ended up with in our answer. So the 6 over 3 would reduce to 2. X to the 4 over x to the third, the 4 minus 3 is 1. We'd end up with exactly the same answer without having to write out and canceling all the terms. Let's combine these together and see what we can get. So in these examples, we have problems that combine the product of powers and the quotient of powers into the same problem. And my advice is to deal with part of the fraction that has multiple terms in it first. So in the first one, we are going to try to simplify 4x squared times 2x to the third first, and then use the quotient of powers rules to try to simplify the fraction further. So for my first step, I am just going to keep the numerator the same since there's only one term there. And in the bottom, I have 4 times 2, which is 8. And then I have x squared times x to the third. So if we use the product of powers rule here, x squared times x to the third is x to the fifth because the bases are the same, we add their exponents. Now we can use the quotient of powers in order to simplify this. We have 2 over 8, which will reduce to 1 over 4. And then there's 4 x's on top and 5 x's on the bottom. So if we subtract 4 minus 5, we end up with negative 1. Well, that doesn't seem like it makes much sense, but what that really means is we're going to have 1 extra x in the denominator. So our solution will have 1 extra x in the denominator. Or if we thought about this in the canceling way, x times x times x times x on top over x times x times x times x times x on the bottom, and we went through and started canceling all these out, there would be 1 extra 1 on the bottom left over after all the canceling is done. And that's why our solution has an x in the denominator still. Okay. Let's move on to 4xy to the fourth, 2 variables, times 3xy. And since we have multiple terms in the numerator, let's simplify the numerator first. I will put kind of parentheses around that to show that we're going to do that first. Everything in the top is being multiplied by each other. There's no addition or subtraction in the numerator. So I can do it in any order I'd like. I would like to multiply 4 times 3, which is 12. Then x gets multiplied by any other x's you see. X times x is x squared. And there are 4 y's here. And that gets multiplied by the 1 y there. There'll be y to the fifth. 5 y's total. And all of that will be over a single y, or y to the first. Now we can use the quotient of powers and simplify. We have y's on the top and y's on the bottom. Now the y on the bottom doesn't go into the 12 on the top, and it doesn't help simplify with the x squared, but there's 5 y's on top and 1 y on the bottom. This bottom y will cancel out one of the top y's, or 5 minus 1 is 4. So our solution will be 12 x squared y to the fourth. Next, we have the power of a product property. And this occurs when we're taking the product of two numbers, like x times y, and then raising that product to a power. Well, we can rewrite that as if we are taking that power and applying it directly to the x and directly to the y. So that can be rewritten as x to the third times y to the third. In dealing with numbers, we can take this fourth power and apply it to the 2, apply it to the x, and apply it to the y. Here we have 2 to the fourth times x to the fourth times y to the fourth. Now, 2 to the fourth can be multiplied out. 2 times 2 times 2 times 2 is 16. So 16 times x to the fourth times y to the fourth. And I'll rewrite that because we don't need the multiplication signs anymore in between. 16 x to the fourth, y to the fourth. I find that the converse of this property is also very useful. Instead of taking an exponent and applying it to a product on the inside, if we have the product of two numbers with identical exponents, so look, that 3 is being raised to the second power and the 4 is being raised to the second power, I can group those together as 3 times 4 raised to the second power. Because they have exactly the same exponent, I can group them together that way. It's like using the power of a product property backwards. And 3 times 4 is 12, so that's like 12 squared. And 12 times 12 is 144. Now this would give you the exact same answer as if you had 3 squared, which is 9, times 4 squared, which is 16. 9 times 16 is also 144. The power of a quotient property says that if you are taking the quotient of two numbers, then raising it to a power, you can apply that power directly to the numerator and the denominator and rewrite it that way. You can't just apply it to the numerator or the denominator, you have to apply it to both. So let's see how this looks. Over here we have 3/4 to the third power, and I can rewrite this as 3 to the third over 4 to the third. 3 to the third is 27, and 4 to the third is 64. Now let's see how this would look if we just multiplied out 3/4 3 times. So 3 times 3 times 3 is 27. 4 times 4 times 4 is 64. We get exactly the same answer, which is good. That's what we're looking for. Okay, let's mix the variables in with numbers themselves. 25x squared y squared. Now this is one of the situations where I'm going to go backwards and try to see if I can pull something out of all of those terms. Now 25, I notice, that's really 5 squared. I can rewrite that as 5 squared. And I'm going to do that. 5 squared times x squared over y squared. Now everything is being raised to the second power here. So I can rewrite this entire problem as 5x over y squared. Now this is using the reverse of the power of a quotient, or the converse of the power of the quotient. In this circumstance, it's almost as if we are factoring a squared out, and this is very useful when we get into Algebra 2 topics such as factoring. The next property we will go over is the power of a power. And this happens when you have a base and an exponent already, and you are raising that to another power. So x to the m being raised to the nth power. When this happens, it's simply just the two powers multiplied by each other. So it's easier to see this in the numbers. 2 to the third to the fourth power. So we have two exponents. We have a 3 here and a 4 here. And when we raise a power to a power, we multiply those exponents. So it becomes 2 to the 3 times 4 power, or 2 to the 12th power. And we can break this down. 2 to the third to the fourth would be like 2 to the third times 2 to the third times 2 to the third times 2 to the third, right? Everything in the parentheses gets multiplied by itself 4 times. Now each of those can be broken up still. So 2 to the third is 2 times 2 times 2. 2 to the third again is 2 times 2 times 2. 2 to the third again, 2 times 2 times 2. 2 to the third again, 2 times 2 times 2. So now that we've expanded this as large as we possibly can, we count. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 2's being multiplied by each other. And they're all just being multiplied, so we can rewrite this as 2 to the 12th. Rather than having to break it apart like that each and every time, we can just remember when you raise a power to a power, the exponents are multiplied by each other. And it'll save you a lot of time and a lot of space on your paper. Now let's do this with a mix between variables and numbers and multiple parts to the term. So we have 2, x to the third, y to the fourth. And I'm going to distribute kind of this 2 to be the exponent or multiplied by each of the exponents. So the first one, the 2 to the first times 3 is just 2 to the third. Then we have x to the third times 3, because we're raising x to the third power. That will be x to the 9th. And finally, we have y to the 4th, and I'll multiply that by 3. That gives us y to the 12th. So this is 2 to the third, which I'll rewrite as 8, x to the 9th, y to the 12th. Okay, now let's combine using the power of a product, the power of a quotient, and the power of a power properties together and see if we can solve some of these sophisticated problems. So whenever you're dealing with any of these more complicated problems, always deal with the power of a power property first. So I'm going to apply this 2 as an exponent to both of these. So that will become 2 squared times x. Now we'll multiply the exponents. 4 times 2 is 8, x to the 8th, and then I will bring along with it this times x to the 4th. All right, I'm already simpler. 2 squared is 4. X to the 8th times x to the 4th. Well, this is the power of products. They have the same base, different exponents. We will add them. That will be x to the 12th. Now down beneath, we have a quotient, and I probably could simplify that quotient first, but I am actually going to apply the power over power first. So I'm going to apply this squared to every single term inside. Whether it has a visible power or not, the 2 doesn't have a visible power, it's 1. I will apply it to all of them. So this becomes x squared is x to the 4th. Y to the 3rd squared is 2 times 3 is 6. Y to the 6th over 2 squared x to the 8th, because 4 times 2 is 8. So we just use the power of the power property, and now we can start simplifying this. I have 4 x's on top, so now we're using the quotient of powers rule. I have, let's see, 4 x's on top, and that will reduce with the 8 x's I have on the bottom. So the 4 on top will actually cancel out, and I'll be left with 4 extra on the bottom. And I will get y to the 6th over 2 squared is 4, x to the 4th. And that's as simple as I can make it. Each of my variables only exists once. Each of my base numbers only exists once. I have a y for a base number in the numerator, and x for the base number in the denominator. There's no numbers that can simplify. That is fully simplified. Cool. Our next property that we're going to talk about is kind of a peculiar one, the zero exponent property. And this states that any non-zero number raised to the power of 0 equals 1. So x to the 0 power equals 1, as long as x is not 0. 0 to the 0 power is an undefined term. But any other number, positive, negative, decimal, fraction, doesn't matter. Any non-zero number raised to the 0 power will be 1. So in our example on the right, we have negative 14 to the 0 power, and we don't have to worry about signs here because the negative 14 is all in parentheses. So that entire quantity raised to the 0 power will be 1. Let's look at it in context of a larger problem. So we have 5x squared y to the 0 power. Now, don't get too creative here. The only base that has an exponent of 0 in this entire problem is y to the 0 power. That is the only thing that will actually reduce to 1. So this will be 5x squared times 1, because y to the 0 power is 1. The 5x squared is not being raised to the 0 power. In fact, x is being raised to the second power, and 5 has the power of 1. 5x squared times 1 is just 5x squared. Now, the trickiest of all the properties is the negative exponent property. And this one states that any non-zero number raised to a negative power equals its reciprocal raised to the opposite positive power. A lot of words there to trip yourself up. This is how I like to think of it. When you have a number raised to a negative exponent, the first thing you want to do is eliminate that negative exponent. So if that number is just a normal number that would normally be, kind of a whole number, it becomes the bottom of a denominator. And the exponent sticks around, but it loses its sign once you move it. So once you move that to the bottom of the denominator, it loses its sign. It becomes 1 over x to the third. So x to the negative 3 power is 1 over x to the third. Now, if it is in the denominator already, so let's say we have 1 over x to the negative 3. Well, it's already in the denominator. We can't move it to the denominator. Remember, the reciprocal flips over fractions, so the denominator will become the numerator, and that will just be x to the third over 1. Notice the sign is gone because we did the reciprocation. So x to the 3 over 1 is just x to the third. All right, this one's going to take a little practice, but that's okay. That's what we're here for. Let's look at an example with just numbers. 6 to the negative 2 power. Well, that's the same thing as saying 1 over 6 squared. Notice we put in the denominator of a fraction, and once we moved it to the denominator, the negative symbol went away because we already performed its operation. And 1 over 6 squared. 6 squared is 36. So that's the same thing as saying 1 over 36, fully simplified. But now let's take a look at this much bigger problem. 3y squared z to the negative 3 over x to the negative 2. Now I want you to notice that every part of this problem doesn't have a negative exponent. There's two parts that have negative exponents, and that is z to the negative 3 and x to the negative 2 power. Now, the numerator z to the negative 3, we are going to move that down to the denominator. And once we move it to the denominator, the negative symbol will go away, but the z and the 3 will both move down. The x to the negative 2 power, which is already in the denominator, will flip upward and become part of the numerator. So let's see how this will look. 3y squared is not affected by any of those negative exponents. The z to the negative 3 will move down to the denominator. We have z to the third in the denominator, and our original denominator had a negative exponent. That moves up to the numerator, becomes x squared on top. So we have 3y squared x squared over z to the third. And actually, there's no more simplification we can do here, because all the numbers have different bases. So here we go. Let's combine together some of these numbers that have negative exponents and zero exponents. And we have a few terms here. Well, it's really all just one big mush of numbers together. But the first thing I always do is deal with any zero exponents, because it will just simplify my problem. I have a y to the 0 there. Any number to the 0 power, as long as it's not 0 itself, reduces to 1. So that reduces to 1, which in this case will just kind of go away. And we'll be left with 3x to the negative 4th times 3xy to the 4th. And I have an x to the negative 4th. I'm going to deal with that next. Remember, the negative 4th is only talking to the base right in front of it, not the 3, just the x. So I'm going to move that 3x to the negative 4th to the denominator. But you might be saying there is no denominator. Well, there will be. Everything that isn't moving to the denominator will be written on top. 3 times 3xy to the 4th. And then the one thing I'm moving down, the x to the negative 4th, becomes an x to the 4th in the denominator. Now we're not quite done simplifying yet. I have 3 times 3, which I can multiply together. And I also have an x on top, which is x to the 1st, and x to the 4th on the bottom. I can reduce those. I can use the quotient of powers rules property on that. So 3 times 3 is 9. My x that's on top right now will cancel out one of these but I will still be left with 3 of them. So my numerator will be 9y to the 4th over x to the 3rd. And that's as simple as I can make that. All of my numbers have different bases. I can't reduce anymore. In the next problem, we have a to the negative 3rd, b squared, all over 2a to the 0 to the negative 3rd. Now there is a lot going on here, but the first thing that is catching my eye is this a to the 0 power. Anything to the 0 power is just 1, as long as the base is not 0. I am going to deal with that right now. A to the negative 3rd, b squared, over 2 times 1 is just 2 to the negative 3rd. All right, now I have one of those situations where I have negative exponents in the numerator and in the denominator. So the negative exponent in the numerator, that one, I am going to move that down to the denominator. And this negative exponent I have in the denominator, I will move up to the numerator. So that's a number, so I'll write that one first. My new numerator will be 2 to the 3rd. I could keep the parentheses around that, but I know it won't change my value anymore. 2 to the 3rd, b squared. And my a to the negative 3rd power, it will move to the denominator. That will become a to the 3rd in the denominator. And I just have a little bit more simplification. 2 to the 3rd is 8. 8b squared over a to the 3rd. And that's all we got. All right, good luck practicing.